Bismillahirrahmanirrahim. Assalamualaikum dear students. I hope you will enjoy the beautiful topic of development length and I hope you will make some kind of practice on those examples which I will did in my last lectures. So we will start our previous example which we will did in Breaker book. In that example I have saw an error which was relating to side cover and top cover. So let's see what was that error. Already I will explain that example in full detail. So the error which I was done in that example, I will elaborate that error right now and you will see what was that error. Okay, so basically that example was not so tricky, was simple example, but the problem is that they count for the wall reinforcement. Okay, so let's see. Where so this was the example, and we did explain all the parts of this example. So today I just want to start uh, example from this place because we did a mistake here. I will consider that 1.5 is up to the face of the main bar and 0.5 is the diameter of the main steel. Actually, if you visit the beam section, this is the beam section. These three are basically number 8 bars. So number 8 bar diameter is 1 inches, and basically you will see these dotted lines, which is basically the wall uh, wall steel bars. Okay, and that is number 4 basically. So the this number 4 bar is basically placed in this wall at a rate of 12 inch center to center, and these 3 bars are basically inside. They are placed inside into these 2 bars. So therefore, whenever we are counting this side cover, this is the side cover. Okay, if I draw the sketch, let's see. So if I draw the sketch, this is the beam cross section. Okay, and those dotted lines, which is right over at one side of both side of the beam, these are the wall reinforcement which is provided to the beam. Okay, and the bars are placed just over here. Okay, so due to these bars, the 1.5 inch cover basically up to the face of this bar. That is basically to the face of this bar. This is 1.5. Okay, this is 1.5, and the bar which is placed over here, its dia is number 4. So number 4 means number 4 divided by 8 give you the diameter and then make it half, so you will get 0.5. Okay, you will get diameter of the half diameter. Uh, no, this should not be divided by 2. Okay, just 4 divided by 8 gives you 0.5. Okay, just divide 4 divided by 8 because you have to cut one diameter of the steel bar. Okay, so once you if I elaborate the section, okay, this is bar, okay, this is wall bar, that is number 4. Okay, this is number 4. So, and this is the beam face. So the distance up to this point is basically 1.5, and the distance up to this, it is equal to the diameter of this number 4 bar. So once you count, you add this 1.5 with this diameter of bar. This diameter of bar will be equals to 4 divided by 8. That is number 4 dia. So that gives you 0.5. So the basic term, which is 0.5, basically comes here from that number 4 bar. Okay. So therefore 1.5 plus 0.5 gives you 2 inches. So as the diameter of the this bar is basically number 8 bar. Number 8 bar. Clear? So number 8 bar diameter divided by 8 gives you 1 inches. So this means that the number 8 bar diameter is 1 inch. So therefore it's this 2 means 2 times of diameter of bar basically. This means that the distance from the face of this steel bar, main steel bar to the side is equal to 2 times. This means you can adjust 2 number 8 bar in this place here. Okay, and this distance is basically this distance is equals to 2 times the diameter of bar. Okay, the clear spacing of the bars is now. The clear spacing means that there are 3 bars. Okay, there are 3 bars which is placed at the top portion of the beam. So what will be the clear spacing amongst these bars? Okay, you can determine it by subtracting, as this is 16 inch. So 16 minus this side cover minus that side cover. Okay, and divide that by 2 because there are 2 spacing, 1 and 2. So therefore 16 minus 2 times of that clear spacing, which we get 2 inches, minus 3 bars. Yep, you have to subtract these 3 bars because you want to get this clear spacing. So you have to subtract these the area for these steel bar also. Okay. So these these 3 are the basically number of bars, and this is the diameter of that bar. Okay, and divided by 2 you will get 4.1, means 4.5 times of diameter of bar. This clear spacing is basically the clear spacing between the bars, between the successive bars, is equal to 4.5 inch, means this spacing and this spacing both, this is also 4.5 and this is also 4.5 inch. Now I think you will understand right now. Okay, so I think up to this point this example is clear. We will explain this whole example in lecture 4. Full detail was given in that lecture. See that lecture, watch that lecture, and you will learn that what is asked in this question and what was needed in this question and what was given in this question. Okay, we are just trap here that from where this 0.5 is come. I will make a little bit mistake in that lecture. So here I will find that error, that what we will did basically. Okay. There are number 3 stirrups outside of the 3 number add bars in the criteria 1. Basically it was given that uh, although this is the wall and this is the beam, so basically in this beam the steel bars are provided here and there are stirrups. At the initial stage there are 3 bars, okay, at the rate of 3 in center to center, and after that the bars are placed. I think the bars are placed, the bars are placed, yep, 3 number add bar, okay, where are the stirrups? The beam has closed number 3 stirrups with equality at a spacing of 7.5 in center to center. Yep, 7.5 in center to center. So this spacing was given, that is 7 number 3 at the rate of 7.5 in center to center. Okay, center to center. So this was the basically the stirrup spacing. So what you will later, you will determine the the distances are, you can check this 7.5 in center to center distance of these bars, okay, the of these stirrups, that whether this spacing criteria fulfill the ACI criteria which is given for uh, which is given for shear design, okay. So you have to check those criteria, that you know you will learn that this is equal to AV, okay, AV Fy into D divided by V by Vs, okay. This is criteria number 1. You have criteria number 2, that S is equal to AV Fy and I think so 50 into W, and criteria number 3 is AV Fy divided by 0.75 B into Fc prime under root, I think, and criteria number 4 was this is equal to D over 2, and criteria number 5 was I think so 24 inches. So you will check these criteria, okay, and if this spacing is lower or is lesser than the amount of spacing which you will get from these criteria, so then it is okay. So in whenever you are using that two cases which is used for the development length formula, so in that cases you have basically some sort of restrictions. In that restrictions, if I go to the table, is the table. Where is the cases which I will explain in full detail, case 1, case 2 and other cases. So basically in that cases you will see that restriction, this is the cases, okay. So basically you will see that this is case 1, okay. In case 1 it is said that clear spacing of bars being developed are spliced not less than dB. So I think that is clear, because the clear spacing in our example is more than diameter of bar, that is around about 4.5 times of diameter of bar. So that's criteria, the first criteria is fulfilled. And stirrups are ties through LD. This means that the stirrups are ties which is used along the development length not less than the code minimum. It means the stirrup or ties must fulfill the ACI criteria, that is the shear criteria, 1, 2, 3, 4, 5 criteria. So if they fulfill this criteria, so you can use this example. Okay, so this case number 1. So we will check if this criteria is fulfilled, so then we will use it. This criteria is not fulfilled, we come to case 2. Clear? And we have to use this formula because our main steel reinforcement are size more than number 7, that is number 8. So basically we will use this formula. Okay, so let's see, we will check the example that what is uh, given to us in that example. Mm, mm. This is the example. They check it because the clear spacing between the bar is not less than 2 dB. Mhm. And the clear cover to the number 8 bar exceeds dB. You know, clear cover, there are number 3 stirrups outside of the 3 number 8 bars, that is clear, almost it is given. Because the clear spacing between the bars is not less than, mhm, is not less than 2 dB. This criteria is not fulfilled here. Okay, means this is the criteria for case number 2, that if the clear distance in between the bars, mhm, in between the bars to 4.5, 4.5, is not less than, because the clear spacing between the bars is not less than 2 dB, and the clear cover to the number 8 bar exceeds dB. Bar development in the wall is governed by case 2. And for, so what does it mean? This means that the clear spacing between the bars, the clear spacing between the bars, by 2, so are 4.5, and we have 2, because although this criteria is met in my view, because it says because the clear spacing between the bar is not less than 2 dB. Yes, exactly, exactly. Okay, okay, because this means that we have this distance is 4.5 inch. Okay, we have this distance between these two bars. This is 4.5 inch. As 4.5 inch is more than 4.5 inch is more than 2 dB, because dB is 1 inch. So 4.5 is greater than 2, so therefore so basically you will check this case number 2. So as 4.5 inch is more than 1 inch, 2 inch, okay, so this therefore it says that 2 dB is not less than, is not less than clear spacing. Okay, it is not less than clear spacing. Clear spacing means uh, this distance, okay, which is face to face distance in between the bars. So therefore case 2 is not work here. Okay, for case 2 it is necessary that this clear spacing should be less than 2 dB. Okay, so we have to use now case number 1. But if you are interested to use case number 1, you have to check your stirrups or ties criteria. So therefore we will check that spacing that whether it is fulfilled that criteria or not. Okay, so therefore that check it. It's equation case number 2, and for number 8 bars equation 812 will apply. Okay, so now we will compute the development length for number 8 bar in wall. Okay, we will calculating this development length, and how much we will embed this steel bar into this wall, how much we will insert, how much length we will this steel bar will we will insert into that wall. Okay, so using the development length formula, which is case number 1, from case number 1, so you know that is top reinforcement, so your side factor will be 1.3. There is no epoxy, so therefore epoxy coating factor will be 1. As there is a lightweight concrete, that is sand based concrete, so for lightweight concrete your lambda factor will be 0.7. Just putting the values in this equation, you will get 82.2 inches. That is your uh, design development length. The bars must extend 82.2 inches, means 7 foot into this wall. From this point A to this point, this is 7 foot distance will be necessary. Okay, to produce its full length. Okay, now compute the development length for number 8 bars in the beam using table. Now in that first part, basically they calculate the development length for it should be remember one thing must be remembered, that you know yes, uh, there are number 8 bars. Okay, there in the portion or beam which is inserted into this wall, the stirrups which is provided to this beam portion is the these wall bars, which is placed at a rate of 12 inch center to center. Okay, now in the beam the stirrups are placed at a rate of 7.5 inch center to center. So here we will check those stirrups criteria. Okay, there are only present bars of wall. Okay, in this wall portion, but here is the basic stirrups which is placed in this cantilever portion. So for that purpose we will check the stirrup criteria are the minimum shear area, that whether the shear area is more than the required, whether is the provided shear area is more than the minimum shear area or not. Okay, so from here it says we know that the clear spacing between the number 8 bars exceeds dB. Okay, this is clear, we know it, that the bars spacing between the bars is more than dB. Okay, and that is also more than 2 dB. The stirrup spacing of 7.5 is less than d by 2. Yes, d, because we have d is equal to 15.5 inch. So the wide 15.5 inch, it comes out to be more than 7.5. Okay, it comes out to be more than 7.5 because 15 is equals to 7.5. So it is 0.5. So 7.5 is more than d by 2 also. But we also need to check the minimum area requirement in ACA report, because we have to check that the stirrup area AB, which is vertically provided to the bars, okay, it is the beam cross section, okay, and there are bars, and you provide basically the stirrups to this steel bars. Now you have to check this stirrup area, that is provided area, and that is equals to, it is denoted by AB. So add the diameter of this bar is number 3. I already mentioned you people that this is number 3 to the right of 7.5 inch center to center. So AB is equal to 0.2 multiplied by 0.11. Clear? So you will get 0.22. Clear? 0.22 square inches is the provided area. Now we will check that this provided AB area, this is provided, okay, whether it is greater than AB minimum. AB minimum is given by ACI code. So ACI code, from here you can get it from this formula. You can get, or you have to check it from this formula also. Okay. So from this formula you will get AB is equal to, as spacing is given to us. So therefore 50 into BW into S divided by Fy. Clear? And you as well you can get AB from this formula also. So what they did, they basically derived AB from this formula as well as from this formula. So select the minimum value from these two. Okay, the minimum value. It will also give you one value. It will also give you one value. Select the minimum value from these two and three criteria. Okay. So basically that is here this process. Okay. AB 0.75 dW into S divided by FYT. Same is thing which I will mention you. That is criteria number 4, and greater than equal to 50 psi into dW into S FYT. So you will get one value from this and you will get one value from this. So select the maximum or the minimum value from this one, from this. Okay, minimum value AB. Okay, so just putting 4000 in this, the second part, this part will give you the required value. Okay, that is 0.15. So as 0.15 is less than 0.22, so A provided is greater than AB minimum. So our ACI code provision is accomplished. Okay, so therefore we can use case number 1. Okay, therefore case number 1, table add 1 is satisfied. Okay, from there you will putting the values. Okay, you will putting the values, you will get L is equal to at point 82.2 inches, which is already uh, achieved in this portion. Okay, so basically in that table case number 1 is applicable. This is the formula. Okay, you will putting the values in this formula, and you will, this is not the formula, that is in millimeter, this is the formula. Okay, so you will get, you have side E psi E Fy 20 lambda Fc prime B, you will get LD, and you will get the required answer, that is 82.2 uh, 82.2 I think answer. Okay, so this was 82.2 inches, which exceeds the length of the beam. Okay. Now this is also a very tricky, a very confusing one, because you have the length of the beam is 5 feet, and the development length which you will get is more than, that is around about 7 feet. So 2 feet length is more. Okay, so therefore we will go to check it from basic formula on development length, that is the basic formula. You will also cross check it. Okay, so in this formula you know all the components of this formula, because in example 1 in lecture 3 I will mention each and every component in very detail. But here at sin t, you know, that is top reinforcement, that is obviously 1.3, this is 0, and size factor as number add bar is used, so therefore you will consider it as 1, size factor as 1, because when it is less than 0.8 will be 6, when it is less than 0.6 main bar, then you will use 0.6, otherwise you will use 1. If C prime given, you have to select CB now, right now. Okay, so from where CBs come, one thing I mentioned you, that in CB there is a little bit confusion, almost all students. that CB basically, if you are considering the clear side spacing, which is from the face of the bar to the face to the outer face of the concrete, and from the face of the bar to the outer face of this. Sometimes, like we will did an example in comic book, so they basically consider this cover to the center of bar. Okay, so you not need to become confused in this calculation of CV, because there is a little bit trick. Okay, if this is your stirrup, okay, which is confined over the steel bar. So if you consider side cover to the center of this bar, side cover to the center of this bar, this is side cover, and you will consider the bottom cover to the center of this bar. Sorry, sorry. Yes, this is your side cover, and this one will be your bottom cover. Okay, to the center of bar. This was done in comic. So then you will basically the clear spacing between the bar, you will get to the center. Okay, you will get the center to center spacing of the bars and then divide it by 2. Okay, then divide it by 2. Okay, this 3, then you will select the minimum value. Okay, this is done basically in Cormac, MC Cormac. Okay, this was basically did an MC Cormac book, an example 7.3, 7.2 and 7. Roundabout in those examples. So basically, uh, page number 180, page number 204, I think so. 204, 204, share design. Yep, this is the example. Okay, if you look and you will search this side cover, you must note this difference. Okay, because some authors consider it as clear spacing and some it considered as center to center spacing. So if you consider center to center spacing, then what are the criteria? Let's see. Look, this 3-inch, which is the side cover, it is up to the center of this bar from the face of the beam, and this 3-inch cover, which is the bottom cover, it is up to the center of this bar. So the third criteria is now from this center to the center of this steel bar, from the center of this steel bar to the center of this steel bar, you will get that center to center spacing and divide it by 2, because you have to consider this clear spacing half of this center to center spacing, and therefore they did it. Okay, therefore they did it. Let's see this one. This is the 1/2 of the center to center spacing. If you don't consider center to center spacing, you will consider the clear spacing. So your clear spacing is roundabout from the face of this bar to this edge, and from bottom cover from the face of this bar to this, and then you will consider the clear spacing. Okay, you will consider this clear spacing. So there is clear spacing or center to center. When you are taking center to center spacing, what you will do, and when you are considering clear spacing, what you will do. Okay, basically. So you must know about this difference. Okay, you not need to be confused. Okay, both give you same result. Clear? So CV here is the smaller of these two. Let's see what that is. The distance from the center of the bar to the nearest concrete surface from the side of the beam to the center of the bar is, let's see, 1.5. You know, this is the bar diameter. No, this is the side cover, clear side cover to the face of the stirrup. Okay. I explained it in the initial stage. 0.5, 0, that is the number 4 at point A, because you must know this value. Okay, this is not basically the stirrup dia, it is basically the number 4 dia. Why it is taken? Because we are calculating the spacing or the side covers at point A, and at point A there is the wall bars, not the stirrup bar, because stirrup bars are placed at a distance is divided by 2 from this base. Okay, so we are calculating side covers at just right over it, the face, this critical section. Okay, this critical section. So at critical section there is a bar of wall, not the stirrups are there. Okay, so you must know this difference. This is a little bit confusion. Okay, you must note this thing. Okay, so 0.5 is clear, and that is center to center distance, because this is the bar dia which is divided by 2. So this 2.5. Now this 2.5 is up to what place? This is basically center to center dia. Okay, this is basically center to center dia from this point to the face of this beam. Okay, this 2.5. So basically they consider center to center dia. If you look to the example number 1 which we did in lecture number 3, so in Nielsen book, so basically they consider the clear spacing. So you people must need to see that example and what this difference. Okay, you to understand this difference, that what is basically it is. Okay, now I think this is clear. 2.5 inch. The other criteria is half of the center to center spacing of bar, which I will did. Okay, half of the center to center spacing. So from where this is come, you must know the difference, that how clear spacing comes out. Okay, how clear spacing comes out. But remember, basically what that is, 16-inch is the beam width. Okay, 2, that is you have 2 clear spacing, 2 center to center spacing, no? 2 center to center spacing. 2.5 is center to center spacing. Okay, so if you subtract this 15 minus 2 multiplied by 2.5, basically what does it mean? This is a little bit tricky. Okay, this is a little bit tricky. You must get practice on it, because it is a little bit tricky. Let's see. Okay, you have, you know, you have you have 3 bars. Okay, you have 3 bars. Okay, and the center distance from this bar to the face of this beam, it is derived in step A, that is 2.5 inch. Okay, okay, and you know this distance is also comes out to be 2.5 inch. Yeah, clear? Okay, now what will be the center to center distance, this center to center distance, this okay, what will be this s? Okay, what will be this s? Clear? You need to determine this s. Clear? You need to determine, this is round about 16 inch. Now your point is that what will be this distance? Clear? And this s will be right here. Okay, this s will be right here. So there are 2 s's. So this means 2s you will get. because this center to center spacing will be equals to this center to center spacing. Okay, so 16 minus uh, if you subtract the basically we at the first step we see that this clear spacing I think so that is 4.5 inch. I think so that is 4.5 inch which we will get. 4.5 inch, yes. So the clear spacing between these bars is 4.5 inch. So if I add this half and this half to the center of this bar and to the center of this bar, this gives me what? This is the dia of this bar is 1, so 1 divided by 2 plus the dia of that bar is also equals to 1, so 1 divided by 2 gives me 0.5, 0.5 is equal to 1, gives me 5.5, I think so. So this is the center to center distance, and it means that this is equal to 5.5. If I divide it by 2, okay, because I need to determine half of the center to center distance. This should be noted. Okay, this is remember half the center to center spacing. Okay, so once you get the center to center spacing, you have to divide it by 2 because you have to take half. So it will give you 2.75. I think so. It will give you 2.75. So that is 2.75. Okay. So if you ignore this step, you can did this step by this process. Okay. After that, now you will check this is more than this one. So your controlling criteria is this one. So therefore, CB is equal to 2.5 inch. You will calculate KTR as we will did in example number 1. 40 is constant, ATR is equal to 0.22. We will determine it. 2 multiplied by 0.11 because number 3 step is there. That is the spacing which is given as 1.5 inch center to center. N is the number of bars which is 1, 2 and 3. Okay. So N is 3. Just putting the values you will get the answer. Okay. Okay. So divide determine KTR. Now you will uh, putting the values of KTR into this CB and DB. You will get the answer of this, and you have to check it. Okay. You have to also check the value of psi t into psi e, which must be less than 1.7. Okay. And you have to check the value of this portion also, CB plus KTR divided by DB, which must be less than 2.7. Clear? So let's see. KTR is 0.39 and CB is 2.89, which is not less than 2.5. So you have to take 2.5. Okay. You don't take 2.89. Okay, you will take 2.5. So 2.5 is taken. Okay, 1.3 multiplied by 1 is already less than 1.7. So that criteria is also fulfilled. That is 1 dB diameter of the bar is 1. Okay, and the rest of thing is same. Okay, you will get 49.3 inches. Okay, the LD is now 49.3 inches. This is the correct answer. This is the exact answer. Okay, so the bar should be extended the full length of the beam. Extend the bar to 1.5 inch from the end of the beam. This means that now the bars can be accommodated into the wall because if this is your beam. Okay, so you have to extend the bar into the wall up to 7 feet. Okay, this is 7 feet. Clear? This is 7 feet. This is 7 feet. Okay, and from there you have to extend it up to you you need to cut this bar at a distance of 1.5. Okay, you have to leave a room, a side cover that is 1.5 inch. This must be ensured. Okay, this must be ensured because development length basically depends on the diameter of the bar as well as side covers. Okay, so these covers are very important. Okay, so you have to let this cover. Okay, and after that you have to ensure this that 5 feet length will be obtained. Okay, so the length will be, now this is your LD length into beam, and this is your LD length into wall. Clear? So this is what they want in this example. I think it is a very interesting example, and you will see uh, at the last stages we will did some kind of examples on this uh, topic also in cantilever beam, but they are related to hooks because sometimes there are restrictions. Okay, our next topic is about hook. So if you, for example, you calculate that length is around about 7 feet and you are providing here a column. So a column is hardly up to 2 feet, okay, up to 3 feet. May not possible that you will provide a 7 feet column, okay. Practically up to 3 feet, 2 feet, okay. Uh, and that will also occur in very high rise buildings. Certainly in our common practice it is around about 18 inches and 12 inches roundabout. Okay, so how you will adjust this 7 feet length, that is also interesting. So there you have to provide certain arrangements, certain facilities. Okay, and amongst them one is the hook arrangement. You provide, you bend this bar at a right angle or at 180 degree. So then they are called hook. So in next lecture, inshallah, lecture 5, uh, we will explain what are hooks, what different types of hooks, and we will what are those criteria for hooks. You know, so we will explain it completely, right? This topic, and you will see that how hooks are designed. Okay, what are standard hooks also. So we will explain this topic. Clear? So up to this point, or up to this topic, you know, if you have any problems relating to development length, bond length, you can contact me. You can ask question, any question, and I will welcome.